Just one fuel bundle of uranium contains the same amount of energy as just over 71,000 gallons of oil. But uranium can't simply be chipped away from the rock it resides in. It must be chemically separated and processed to make it into usable fuel for a nuclear reactor. Acid dissolves the uranium, but not the rest of the rock. It settles to the bottom of these tanks. The uranium acid solution flows forward, leaving the unwanted minerals behind. Using a series of chemical reactions, they further purify the uranium. They then roast it at 1562 degrees Fahrenheit. This concentrates it into a jet black powder. The uranium powder flows into 55-gallon steel drums. A worker taps the lip of the drum to remove residual powder. He then puts the lid on and activates a press that secures it tightly to the drum. As an extra precaution, he seals it with a steel ring. He labels it to indicate the drum's contents, weight, and radioactivity. Workers stack the drums in a warehouse to await shipment to the next processing plant. There, the uranium goes from black to yellow as they convert it to uranium trioxide, an interim chemical form in the processing chain. They ship the uranium trioxide in specially designed inverted cones. Upon arrival at the next facility, a valve opens at the bottom and the powder flows into conveyor tubes that take it into the plant. Inside, workers dissolve the uranium trioxide powder in acid. A worker takes a sample to test the density and the chemistry and confirms that both are acceptable. They then add a chemical to turn the dissolved uranium back into a solid. After more processing, the uranium trioxide becomes uranium dioxide, the chemical form required for nuclear fuel. Spinning the uranium dioxide mixes the different sized particles to make it a more homogeneous blend. The chemical processing has also caused the uranium to change color again. It is now a fine black powder. Using several tons of pressure, tools shape the uranium dioxide into pellets. A revolving wheel with protrusions guides the pellets into a channel conveyor. The conveyor takes the pellets into a furnace. Over 24 hours, the heat removes pores in the pellets. The pellets shrink, increasing the density of the uranium. The particles fuse together and harden into a ceramic. Here is a pellet before and after baking. A robot arm now loads the pellets onto a tray and levels them. A conveyor moves the tray forward. Ahead, another robot places zirconium fuel tubes on a rack. Zirconium is a metal that's highly resistant to both heat and corrosion. But neutrons will pass freely through it during the fission reaction. The rack of tubes meet up with a tray of incoming pellets. A robotic loader pushes the stack of 30 pellets into the tube. Another robot delivers the rods, one at a time, to an automated welder that caps the ends. The next robot retrieves the completed uranium fuel rod and transfers it to an assembly fixture. It arranges a total of 37 rods in an upright position within the fixture. After the rods have been welded and the bundle capped at both ends, a robot transfers it to a scale. This weigh-in confirms that there is the correct amount of uranium in the bundle. Prior to burn-up in a reactor, the amount of radioactivity emitted by nuclear fuel bundles is very low. and they're safe to handle as workers prepare them for shipping. They're now on their way to the power plant, where they'll be sure to generate a reaction.